You find it on a walk, in a dry riverbed maybe, or sticking out of a cliffside after a storm. It doesn't look like much. It's the color of dirt and rock. It feels like a rock. Heavy, solid, ancient. But the shape is wrong for a rock. It has curves, it has a specific undeniable form. It's a bone, just one. A piece of a thigh bone, a femur. And you might think, what is this? A cow? A deer? It's old, sure, but it's just one bone. What can it really tell us? The answer is almost everything. That single piece of fossilized bone is not an object. It's a book, it's a library. It contains stories of an individual, a species, a world that no longer exists. Paleontologists, the people who study these things, are not just bone collectors. They are readers. They have learned the language of bone, and they can translate that single, silent femur into a detailed biography of a life lived millions of years ago. Let's start with the most basic question. Who did this bone belong to? The first clue is its shape, its morphology. Every bone in a body is shaped by its job. The job of a femur is to support weight and allow movement. How it does that job reveals the kind of animal it came from. A paleontologist would lay this fossil on a table next to the femur of a modern human, a chimpanzee, a baboon, a bear. They would compare every lump, every groove, every angle. A chimpanzee's femur is relatively straight. It hangs down from its hips, designed for a creature that spends a lot of time on all fours or climbing in trees. But a human femur is different. It doesn't go straight down, it angles inward from the hip to the knee. You can feel it on your own leg. This angle is called the bicondylar angle, or the carrying angle. Why the angle? It's about balance. When you walk on two legs, you transfer your weight from one foot to the other. To do this efficiently, without toppling over or waddling excessively, your feet need to land close to your body's center line. That inward angle of the femur places your knees and feet directly under your center of gravity. It's a critical piece of engineering for bipedalism, for walking upright. So if our fossil femur has that same inward angle, that's our first huge clue. This wasn't a knuckle walker. This wasn't a creature that lived in the trees. This creature walked on two legs. It was a hominin, a member of the human family line. Just by looking at one angle on one bone, we have placed its owner in our own evolutionary history. We have learned how it moved through its world. It walked. But there's more. Look at the top of the femur. There's a ball, the femoral head, that fits into the hip socket. In humans, this ball is very large, and the neck connecting it to the main shaft of the bone is long and thick. This is because walking upright puts immense stress on the hip joint. All of your upper body weight is channeled down through those two small joints. A long, thick femoral neck is a buttress, a support structure to handle that stress day in and day out. Chimpanzees have a much smaller femoral head and a shorter neck. If our fossil has the human-like pattern, it confirms our suspicion. This was an upright walker. Now we know how it moved. We know it was one of our ancestors or a close cousin. But what did it look like? That one bone can tell us that too. There's a direct relationship between the length of a femur and a person's total height. Forensic scientists use these formulas all the time on modern skeletons. Paleontologists have adapted them for ancient hominins. They can measure the length of the fossil femur, plug it into an equation, and get a reliable estimate of how tall its owner was. Was this a small ancestor like Lucy, who stood just over 3 feet tall? Or was it a later larger hominin like Homo erectus, who was built much like us? The bone's length gives us a stature, an outline. Then we can look at its thickness. How robust is it? The shaft of the bone isn't just a simple tube. It's a thick outer layer of cortical bone. The thickness of this layer tells us how much stress the bone was built to withstand. By measuring the shaft's diameter and the thickness of the cortical bone, we can estimate body mass. We can start to say not just how tall this individual was, but how heavy, how muscular. Were they slender and wiry, or were they powerfully built? So now we have a picture forming. For one bone, we have a hominin of a certain height and weight who walked the earth on two legs. We have moved from a simple who to a more detailed what. But what about the individual's personal story? How old were they when they died? Bone tells us this too. Our bones grow throughout our childhood and adolescence. The long bones, like the femur, don't grow from the middle out. They grow at the ends, at specific places called growth plates or epiphyseal plates. These are areas of cartilage where new bone is laid down. The main shaft of the bone is called the diaphysis. The caps at the end are called the epiphyses. In a child or a teenager, these caps are not yet fused to the shaft. There's a visible line of cartilage between them. This allows the bone to get longer. As we reach skeletal maturity, usually in our late teens or early 20s, these growth plates close. The cartilage turns to bone, and the caps fuse permanently to the shaft. The line disappears. If our fossil femur is complete, we can look at its ends. If the caps are completely separate, we know this was a child. If they are in the process of fusing with a visible line, it was likely a teenager. If they are fully fused with no line visible, we know we're looking at a skeletal adult. That single bone can tell us if this was a life cut short in youth or one that reached physical maturity. For older adults, the clues are more subtle. Bone is living tissue. It's constantly being broken down and rebuilt throughout our lives. As we age, this process can slow down and the bone can become less dense. By looking at a cross-section of the bone under a microscope, scientists can count structures called osteons. The number and density of these can give a rough estimate of age in an adult, though it's less precise than looking at the growth plates in a young person. So we have a bipedal hominin of a certain height and weight who died at a certain stage of life. The picture is getting clearer. But what was that life like? Was it hard? Was it easy? Was this individual healthy? The bone surface is a medical chart. It records injury and disease. Imagine there's a thickened, lumpy area on the shaft of the femur. This is likely a callus, the telltale sign of a healed fracture. It shows that this individual broke their leg at some point in their life, but the key word is healed. A broken leg for an early human, millions of years ago, could easily be a death sentence. You can't run from predators, you can't walk long distances to find food and water. A healed fracture means this individual survived, and that implies something profound. They likely didn't survive alone. For that bone to heal, a process that takes weeks or months, someone else probably had to help them. They brought them food, they protected them. This lump of bone becomes evidence not just of trauma, but of social care. It hints at a community, at compassion. Other marks tell other stories. Small porous holes in the bone or areas of inflammation can be signs of infection. Something like osteomyelitis, a bacterial infection of the bone itself, leaves a permanent scar. We can see if this individual suffered from chronic, painful diseases. The ends of the bone, where they meet the knee and the hip, can also show wear and tear. Polished, shiny areas or bony growths around the margins of the joint are signs of osteoarthritis. This tells us about the physical stress the individual endured, a life of constant walking, running, and climbing taking its toll. Even periods of hardship during childhood are recorded. If a child suffers from severe malnutrition or a serious illness, their body diverts resources away from growth to just survive. This can cause a temporary halt in bone growth. When the child recovers and growth resumes, a thin, dense line of bone is left at the growth plate like a tree ring. These are called Harris lines. If we take an X-ray of our fossil femur and see these lines, we know this individual survived periods of famine or disease as a child. The bone remembers the struggle. The story is now incredibly rich. We have an individual of a certain species, a certain size, a certain age. We know they walked upright, we know about their injuries, their diseases, their childhood hardships. We even have hints of their social structure. But we can go deeper. We can go inside the bone itself to the level of atoms. And that's where we can learn what they ate and where they lived. Bone is made primarily of a mineral called hydroxyapatite. As an animal lives, the atoms that make up its food and water are incorporated into this mineral matrix. You are what you eat is literally true for your skeleton. Scientists can analyze the chemical composition of the fossilized bone to read this atomic record. One of the most powerful techniques is stable isotope analysis. Atoms of an element like carbon can come in slightly different versions or isotopes. Most carbon is carbon-12. A tiny fraction is a slightly heavier version, carbon-13. Plants absorb carbon from the atmosphere through photosynthesis, but they do it in different ways. Trees, shrubs, and herbs in temperate climates use a process called C3 photosynthesis. Grasses in tropical and subtropical environments like the savannas of ancient Africa use a different process called C4 photosynthesis. These two processes absorb the light and heavy carbon isotopes at different ratios. C4 plants, the grasses, end up with a higher proportion of carbon-13 in their tissues. So, if an animal eats a diet of C3 plants' leaves, fruits from trees, its bones will have a certain carbon isotope signature. If it eats a diet of C4 plants, grasses, or seeds from grasses, its bones will have a different, higher C13 signature. And if an animal eats another animal, the carbon signature of the plants at the bottom of that food chain gets passed up to the predator. By drilling a tiny pin-sized sample of powder from our fossil femur and running it through a machine called a mass spectrometer, we can measure its ratio of carbon-13 to carbon-12. This tells us what our ancestor was eating. Did they have a diet like a chimpanzee, mostly based on fruits and leaves from a forested environment? Or did they have a diet that included foods from the open savanna, like grasses, seeds, or the animals that ate that grass? This is a huge piece of the puzzle. The shift from a forest-based diet to a savanna-based one is a major theme in human evolution. It tracks our expansion out of the woodlands and into new, more challenging environments. That single bone can tell us where this individual fit into that grand transition. It tells us about their habitat, not in a general sense, but specifically. This person, this individual, lived and ate in a world with these kinds of plants. But we can learn even more about their world. Other isotopes, like strontium, tell us about geography. The strontium isotope ratios in rocks vary from place to place depending on the local geology. As rock weathers, these isotopes get into the soil and the water. Plants absorb them. As animals eat the plants, the local strontium signature gets locked into their bones and even more so into their teeth. By comparing the strontium ratio in our fossil to the ratios in the surrounding geological formations, we can ask a fascinating question. Did this person die where they grew up? Our tooth enamel forms in childhood and doesn't change, so it holds the strontium signature of an individual's birthplace. The bone is remodeled throughout life, so it reflects the geology of where an individual lived in the years before they died. If the strontium signature in a femur matches the local geology, it suggests the individual was a local. They lived and died in the same general area, but if it's different, it means they migrated. They grew up in one place, with one geological signature, and moved to another. This opens up incredible questions about the movement of early human populations, about social patterns, and about how they explored and colonized their world. All from a few atoms inside one bone. So now, let's step back and look at what we have. From a single piece of a femur, we have identified our subject as a hominin. We know it walked on two legs. We have estimated its height and its body weight. We know if it was a child, a teenager, or an adult when it died. We have read its medical history and the scars left by fractures, infections, and arthritis. We have seen the echoes of childhood hunger or illness. Through chemistry, we have reconstructed its diet and, by extension, the environment it lived in. Was it a forest, a savanna, or a mix? We may even know if it migrated during its lifetime. We have a biography, a stunningly detailed story of one life. But the story doesn't end there, because this bone is not just an individual. It's a data point. It's one piece of evidence among thousands that, when put together, allow us to tell the much larger story of human evolution. Imagine our femur is dated to 3.2 million years old, the same age as the famous Lucy fossil. It confirms that hominins of that era were fully committed to walking on two legs. Now imagine we find another femur from a million years later. Maybe this one is longer, suggesting a taller stature. Maybe its shaft is thicker, suggesting a heavier, more robust body. And maybe its carbon isotope signature is different, showing a greater reliance on meat or savanna-based foods. So, by comparing these two bones, separated by a million years, we can see evolution in action. We can track the changes in our ancestors' bodies as they adapted to a changing world. We see them getting taller, we see their diet shifting. Each new bone that is found fills in another part of the picture. That's a new paragraph, a new chapter to the story. The single bone connects the individual to the entire history of our species. The angle that shows it walked upright is part of a trend that began more than 6 million years ago, a trend that ultimately freed our hands. Free hands allowed us to make tools. Tool use and changing diets are linked to the eventual growth of our brains. The story of that big brain, the thing that makes us uniquely human, has its roots in the kind of posture that is recorded in that femur. The evidence of a healed fracture hints at the deep origins of social cooperation and empathy, the very things that bind our societies together today. The chemical signature of diet tells a story of climate change and adaptation, of our ancestors surviving and thriving as the African forest shrank and the savannas spread. It's a story that continues today as we face our own challenges of a changing planet. That's how a single bone can tell us so much. It works on so many levels at once. It's a tangible link to a specific person who lived and breathed, who felt pain, who got sick, who survived hardship. They were not a faceless member of an ancient species. They were an individual with a life story, and that bone is their autobiography. And at the same time, that bone is a piece of a giant puzzle. It helps us understand the physical and behavioral shifts that made us who we are. It provides the hard, physical evidence that turns the abstract idea of evolution into a concrete reality. You can hold it in your hand, you can touch the place where the muscle once attached. You can see the angle that made walking possible. So the next time you see a fossil in a museum, don't just see it as a brown rock-like object behind glass. See it for what it is. It is a time capsule. It is a message from a lost world. It is the story of a life. And it is the story of all of us. All of that written in the simple, elegant, and profoundly talkative language of bone.